So have you ever used the tree regression tree, random forest, boosting, bugging, XGBoost, any of the model?
Yeah, I used XGBoost to compare to my linear regression last semester at my the final project, and it outperformed
Oh,
my
okay,
linear
that's good.
regression.
Yeah, okay, that's great. So XGBoost is a tree-based method, which is pretty popular, for example, in the data competition. So it's a more enhanced version of the tree method. So we study everything from scratch. So what is the tree-based method? And what is the random forest? What is the boosting? And so on. Yep. Do you have any other comments? No. Okay. So the first thing. So yep. So the tree-based method is a framework for regression or classification by simple split of variables. So this is to explain the salary of baseball players. I think that this is the log scale of salary by years of experience and the number of hits in the last season. Then I think the years of experience, no, okay. The other way, yes, no, yes. So if we want to explain salary by these variables, the best way to separate it into three cases is this. So at first, we check if the years of experience is less than 4.5 or more than 4.5. I think this data is the integer valued data. So no means the years of experience is 1 to maybe 0 to 4. And this is 5 or larger. So if the years of experience is smaller, lower, shorter, then average salary is 5.11. So this is the log scale of salary. So the I don't know exactly what the 5.11 means, but the salary level in logarithm scale. Then if years of experience is more than or equal to 4.5, then we have two cases. The number of hits is less than 117.5 or more than 117.5. If the number of hits is larger, then salary is higher, on average, the 6.74. If lower than that, the average is 6.00. So this is the best way to categorize the entire group into three. So predictor space have the two variables, the years of experience and hits. So that means that this is years of experience and this is number of hits. So at first, so the best way to separate these cases is at first the years of experience. Okay, so 4.5. Then after that, the number of hits. So more than 4.5, then we separate this. Then average is 6.74 and 6.00, and this is 5.1. So this is how the tree is, how the tree is, what tree means. Okay. So it's not really the smooth curve, so not really a linear function or quadratic function, but in some sense, it's step function. But since we have more than one predictor, we consider one predictor at a time, then we optimize the split. Yeah. Oh, actually, the same graph here. Yeah. So this. So average is 6.74 and 6.00 and 5.11. Okay. So in general, if we have more complicated graph, I mean, we further split the tree into more cases, then that becomes this. So how many? So previous one that we have the three cases. So we say the three nodes, but in this case, we have how many nodes here? you can see that we have more split. So we can see that we have the 1, 2, 3, 4, 5. So we have 5 nodes. It's not clear that what is the first split. Probably maybe that we divide here first, maybe. Then after that, maybe we split maybe here, and the third, maybe we split here, and the fourth split maybe here. So in this way, that we have the 5 nodes. So if tree becomes larger, it can be more complicated, the rule. So the question is how to determine the size of tree. So the tree with 3 nodes or 5 nodes, 10 nodes. And the criterion is here. So at first, the important thing is the error size. This is the sum of squared errors. So in the previous example, that we have the salary level for each group. The one is 6.74, another is 6.00, and the other is 5.11. Then we have observations. If observations are 6.9 and the 6.8 and the 6.6 or something, then we can take the difference between these observations, for example, the difference between this and this and this and this and this and this, and we take square, then take summation. Then if that amount, that quantity is minimized, then that is a better tree. So this is the error size. And the second term is the size of tree. So this is the size of tree. And alpha is some parameter, hyperparameter, that is a constant. So we penalize. Large tree. So if the rule is more complicated, of course, we can explain the more variation. But the basically simpler rule is better. So we penalize the size of the tree. So the same idea as AIC. So AIC penalized the model complexity by the number of parameters. So here that we have the actually the number of split. Yeah, basically the same thing. So that maybe the number of split is the number of node minus 1, but the yeah. So we penalize that size. Yeah. So alpha, we have to optimize this by cross-validation. Since this is a hyperparameter. But once alpha is fixed, then we can determine what's the optimal tree. Yeah. So usually that we make a large tree, then that we make it smaller to see if this function, so this objective function, gets smaller. Yeah. Yes.
Sorry, Professor, I didn't understand the difference between yi and y hat rn. Could you please explain again?
Sure. Sorry. This is the class average. So this corresponds to this. And so this is each observation. So it corresponds to these numbers. So we take the difference between the class average y hat sub rm and each observation yi, and take square and take summation. Is it okay, or do you need a little more?
It's clear. No, that's
fine. Okay,
yes.
Great. Yeah, sorry, maybe I should mention that. Yes.
No, thanks. It's fine.
Yep. So this is the case. Yeah. So basically, we have to think about the range of models. So So consider, for example, remember the linear regression with the many predictors. Then we have to optimize, for example, the degree of polynomial regression. Then we try the degree 1 to degree 10. Then we choose the optimal one in terms of AIC. And that may be 4 or 5, but we have to investigate a certain range from maybe p is equal to 1 to 10. So the tree, it's the same thing. So at first, we split the cases many times, and we make a large tree. Then we prune it to make sure that we can minimize the dysfunction, this dysfunction. Yeah. Yeah. So that's it. And so the summary of the building a regression tree. So at first, I make a large tree that based on the method. So basically, we have to try the all possible split and to minimize the sum of square errors. Yeah. Then estimate alpha by cross validation. So what's the best alpha? Then prune the tree to get the optimal tree. So at first, we make a large tree. Then based on alpha, we have the size of tree. If alpha is large, penalty is large, so tree is small. And alpha is small, then tree is large. So we try the different alphas to optimize the value of alpha by cross-validation. Then once the alpha is determined, we can determine the optimal size of the tree. So this is the procedure to fit the tree. So in this way, that we can avoid the overfitting. Yeah. So this is the way. And the cross-validation, if the cross-validation takes too much time, basically, we can do a simpler approach, such as the training and test sets approach. But as long as you have enough computational power for the data set, then you can try the cross-validation. Yeah, so basically, if the training set is small, then we have a lot of trouble. So for example, in the data set D, we have the variable x1, x2, x3, and x1 only have the two values, 0 and 1, and maybe 0, 1, 1, 0, 0, 0, 0, 0, 0, and 0, 0, 1, 1. If we only have 4 observations with x1 is equal to 1, and if you use training and a test set approach, maybe the one set does not include, training set does not include any observation with x1 is equal to 1. So in such a case, we cannot decide whether or not x1 is useful. So basically, we want to have a larger training set. So that means the cross-validation is better. If we use tenfold cross-validation, basically we use 90% of the data as training data set each time. So cross-validation is recommended. Yeah, and this is for the regression model. So basically, we predicted salary in the first example, and the salary is numeric variable. So that's why this function, the sum of squared errors, makes sense. But if this is the classification problem, that we cannot take the difference and take square. We cannot do that. So in such a case, we have to have slightly different function. So what happens if we want to apply the tree method to binary or categorical response? Then for binary case classification problem that we can use this deviance. So basically that we use so if we have the binary problem and label 1 and label 0, then we can count the number of correct label and number of the incorrect label, then we calculate this. So this is basically the likelihood, log of likelihood function, -2 times log of likelihood function. So you can see that the pi to the power NIPI times 1 minus pi to the power Ni times 1 minus pi is the likelihood of the so the likelihood of the the 1 p1 pi and pi so NIPI. So this is the likelihood of the binary case. Maybe we can try some examples. So suppose that we have the probability. So probability of y is equal to 1 is equal to pi observations of which pi is ni over so this suppose that this probability is pi and the probability of y is equal to 0 is equal to 1 minus pi. Then suppose that we have ni observations. Ni is the number of label 1. Okay, so Ni is the number of observations with y is equal to, maybe yi is not appropriate, so maybe y is equal to 1. And that means that capital Ni minus Ni is the number of observation with the y is equal to 0. So in this case, the likelihood of these observations is the pi to the power Ni times 1 minus pi to the power Ni minus Ni. Right? Because if the probability of y is equal to 1 is equal to pi. So if we observe one observation of y is equal to 1, then likelihood is pi. So if we have ni observations, then that is pi to the power ni. So we assume observations are independent. And if y is equal to 0 for this number of observations, then the likelihood is 1 minus pi to the power ni minus ni. For one observation, the probability is 1 minus pi. So we multiply this ni, capital Ni minus the lowercase ni times. So then this becomes actually this function. And if we take logarithm, then that becomes this. So this is the likelihood function, and this pi is given for each node. So each the case. So the last time that we split the entire predictor space into 3 parts. So for each region that we assign the pi. Okay, so maybe this is okay. So I would say that the I is equal to 1, 2, 3. I is equal to 2, I is equal to 3. So each region that we assign the probability pi. So for each each node or each region of the predictor space that we calculate this one. Then we take the summation. So before taking logarithm, that is product. But after taking logarithm, that becomes summation. So this is the same as the likelihood function. So this is called the deviance. So we wanna minimize this quantity. So basically, it's better to maximize likelihood, but this is negative 2 times. So if this value is minimized, then error is smallest in likelihood function. And another way is the error rate. That is the more maybe simpler way to do it, and just assign some conclusion. So I is equal to 1, then we predict y is equal to 0, for example. Then we can determine, okay, so suppose the pi is, okay, so p1 is less than 0.5, for example, p1 is equal to 0.4, then we can read this result as the probability, so the estimated y is equal to 0. Okay, so y hat I is equal to 0, okay, because this probability is less than 1/2. Then using this criterion, you can see how many observations are classified correctly. So if in this region we have the 7 observations of 0, so y is equal to 0 for 7 observations, and y is equal to 3 for y is equal to 1 for 3 observations, then we have the 7 correct decisions and the 3 incorrect decision. So we can calculate the error rate. Actually, we can do that for each region. Then we can count how many of them are predicted correctly. Then we can calculate error rate, and we can optimize the error rate. So we can replace the first term of the objective function by deviance or error rate.
I have a question, Professor.
Yeah, sure.
So the less absolute value for deviance means better model?
Mm-hmm.
Okay.
Sorry, what's your question? Sorry.
The less absolute value for deviance entropy means better model?
Yes.
Okay, thanks.
Yeah, because the larger likelihood is better. So negative 2 times likelihood, the smaller is better. So smallest deviance is good. Yep. Yeah. But of course, this second term still remains. So this term, of course, we have to consider this term. So this term we have to consider, but this yellow part is replaced by the deviance, and the smaller deviance is better. But we have to, balance between the deviance and the size of the tree. So smaller size is better, but also the smaller deviance is better.
Is the deviance negative or positive?
Actually, it does not really matter. But
so if it's negative, would it be like a negative 10 deviance is better than a negative 5 deviance?
Oh, I mean yeah. So okay. So if the deviance is negative 10, negative 5, 0, 5, 10, then the negative 10 is the best. Okay. But I think this is still positive, probably, that we can see. Yeah, that's an interesting question. Log of pi is less than 1. So this is negative value. And this is also negative value. And this is also negative. And NIPI, this is basically the number of, these are counts. So this is positive. And this is positive. So that means that always the deviance is non-negative, right? Negative times negative for each term. So that should be positive, at least non-negative. Yeah. So actually, this case, we don't really have to account for this case. But anyway, the smaller is better. Deviance is non-negative. Yeah, smaller is better. So hypothetically, if -10 and -5, -10 is better. But actually, this is never negative. Okay. Yeah, and error rate we can define for k categories, but the deviance, to extend this idea to k categories, that we need some adjustment. So I think we don't cover this, but the textbook mentioned some ways. Basically, we need some assumptions. Right? Okay, so this is the basics of the trees. So now that we compare the tree-based methods with linear models, so which is better? Relative performance of linear models and tree methods. That depends on the data. So we have several cases, and this green and this is the true. Okay, so at first, this is the classification problem. And the truth is the one for the green area and the yellow for is the sorry, the truth is 1 for green area and the truth is 0 for yellow area. So we think about the first, so this is example 1, okay, and this is example 2. And for this example 1, linear regression, I mean, this is classification, so logistic regression fits better. And this is the boundary by linear regression or logistic regression. So this is the boundary by logistic regression. Yeah, or linear regression if 1 and 0 are interpolated as numbers. And in this case, the linear regression works better. And these black lines are boundary determined by tree-based method. So since the truth is true boundary is straight line, the logistic regression or the logistic regression that identified the true boundary very easily. But if we use tree-based method, so this is basically all boundaries should be the parallel to either x1 axis or x2 axis. So that means that we have to develop very complicated rule that okay, so here we have 0 and here we have 1. But this cannot be optimal because we have some areas, I mean, classification errors. So this area, this area, this area, still we have classification errors. So for example 1, the logistic regression works better than the tree methods. But what happens when the example 2, for example 2? So example 2, the true boundary is here. So if we use logistic regression, the boundary is always linear. There's a boundary for p is equal, the y is equal to 1 and y is equal to 0. That should be a straight line. So that we make this boundary. We make this boundary. So boundary by logistic regression. So it has some errors. You can see this area and this area are misclassified. But if we use the tree-based method, so this is the tree-based method, tree regression, then actually we can get the perfect boundary. So this is better. So here this is better, but here this is better. So it really depends on the problem, which model is better. Yeah, so it really depends on the case. But at least the tree method, the tree regression tree is more flexible for more complicated boundary. Yeah. Yeah, but still, it's not clear. For example, if we use maybe quadratic term for logistic regression, possibly that we can improve the situation. So logistic regression, just a naive logistic regression can make only the boundary, which is straight line. But if we think about the x1, x1 square, x2, x2 square, and the x1, x2 as predictors, then it can do the classification problem better than this. Maybe boundary is pretty close to this. Probably we cannot get this boundary, but maybe we can get this kind of boundary. Yeah, so another consideration is this. So the logistic regression with the more predictors or the tree-based method. Yeah, so some advantages and disadvantages of tree methods. So results are intuitive and displayed graphically. So this is one strength of tree method. So we can split at first, in the first example, we can split all baseball players by the number of years of experience. So that is pretty intuitive. And after that, we separate the experienced players into two groups. The player generating more hits or less hits. So it's pretty intuitive. And no need to create dummy variables for categorical predictors. So suppose that we have the predictor x1, which have the three categories, A, B, C. So we have observation 1 to 100, and the value of x is ABC, ABC, maybe BBC or something. Okay, then we have three categories. Then how to make split of this x1? Basically, the algorithm consider all cases. So that means the A versus BC, and B versus AC, and C versus AB. Okay. So basically, the algorithm decides everything within this estimation of the tree. So you don't really have to create dummy variables. So that is a strong point. And I believe that if we have the too many categories for one variable, for example, x1 has the 200, maybe 100 categories, then basically we have the 2 to the power 100 combinations. Right? So if we have 100 categories, we divide 100 categories into two groups, maybe capital A and capital B, and how many of the categories are in group A and how many of are group B. We have the 2 to the power 100 ways. So they have some algorithm to optimize it. So probably that they don't, our algorithm does not try all combinations, but probably they split it into half and half and do something. So they have some concrete algorithm when we have too many categories. But anyway, so except for that algorithm, we don't really have to create the dummy variables. So that is one positive aspect in some sense. Because if we have too many categories, then we have too many dummy variables. So linear regression, simply we cannot, we really cannot do that, right? If we have too many parameters, we cannot estimate. Yes, that's the case. Yeah, I don't know. Yeah, but still, we have to try many combinations for regression tree. So I don't know if this is the real strength or the just yeah, it's not entirely clear. It's not entirely clear, but at least we don't really have to worry about it as long as we have this algorithm. And the disadvantage is prediction performance is generally not high. Yeah, so the more advanced methods such as random forest, XGBoost, the performance is better, but the naive, the tree method, usually the performance is not really good. So you can imagine that we just investigate the relationship between maybe the height and width of some shells. Then suppose that is almost proportional, then maybe straight line represents the pattern better than just the splitting the entire predictor space into several pieces. So tree-based method, the estimated the value is not smooth, so sometimes it's not good. And not robust, small change in data change result dramatically. So you can think about the situation that we have just the x1 and then we have the categorical value, maybe numeric value y, maybe x and y, and the observations are like this. Okay, then what is the optimal tree? Then okay, so we have the 6 observations here, 6 observations here, 4 observations here. So 4 observations, it's smaller. So we actually ignore it and then we split into 2 groups. So group A and group B. Node A and node B. But suppose we have maybe five observations. Maybe that is more extreme. So yeah, 5 observations, and still the 5 is smallest. 5 is smallest. So the boundary is here, the blue line. But if we have just 2 additional observations, here and here, the data set doesn't change much, but the boundary comes here because the 7 is larger number than 6. So we ignore this part and the boundary becomes here. So that means the boundary isn't really robust. If we change a very small amount, some observations by very small amount, then boundary dramatically changes. And methods often suffer from overfitting. Yeah.
Which of these model needs more time consuming, or I don't know, need more calculation? Linear regression or tree regression?
That's a good question.
It depends on data, or
yeah, so if one variable, I believe that the linear regression is much faster. But the more than, so many variables, the possibly tree regression is faster. Because the linear regression, we have to take the inverse matrix or large inverse matrix. Basically, we need the P by P inverse matrix for linear regression if we have P predictors. But the tree-based methods, we only consider one predictor at a time. So if we increase the number of predictors, then just the required time increases in the same order of P, right? Not the P times P. So I think that for smaller P, the linear regression is faster. The very large P, the tree regression is possibly faster. Yeah. Yeah, so linear regression isn't really working well if the number of predictors is too large. So yeah. And I'm not exactly sure that what so how much time it takes to fit the tree regression. It really depends on the sample size, right? So if n is larger, then at least the algorithm that requires the time proportional to the sample size. But that's still the same as linear regression. Linear regression still the estimation time is proportional to n, except for the inverse matrix. So yeah, I think so. The answer is that it depends on p. Large p, the tree is possibly faster. Okay, so yeah, so that is the regression tree, the basics of regression tree. So we have some positive part, but we have many negative parts. So we have some methods to improve the shortcomings. Yeah. So we have several ways to improve the shortcomings of the tree method. So we study the bugging and the random forest and the boosting. So tree-based methods have a high variance. So just the previous example explains it. So small difference in data set makes the large difference in result. So we have the large variance. Yeah. So the split is largely determined by chance in this case. Of course, in some cases it's stable, but in some cases it's very unstable. So these are the possible remedies. So the first one is bugging. So randomize the training set to make a tree and repeat the procedure and take the average. So yeah, so randomize the tree set, the training set to make a tree. So in this case, okay, so suppose we have large population with maybe 300 observations. Then we randomly picked up some observations. Then sometimes the boundary is around here or around here, around here. And sometimes the boundary is around here, but probably the either of these. And if we take the average of all results, then probably that we can get the more smooth curve, such as maybe like this. So that makes more sense. So bugging is randomized training set to make a tree and repeat the procedure and take average of the many trees. And the random forest, it's similar to bugging, but each randomized sample that involves fewer predictors. So suppose we have x1, x2, x3 up to x10, then the random forest only allow for example, the two splits, the two variables to consider. So we restrict. We can only use x1 and x6, for example. Then we consider the location of a split using only x1 and x6. Then next time, maybe we only use x3 and x10. And next time, maybe x1 and x5 and so on. And it sounds the worse than bugging, but actually it gets better. I'm not an expert, so I don't really understand entirely, but the idea is that if we use bugging, all trees are very similar. But the random forests, the trees are different because we only allow to use randomized predictors, only a few of the predictors. So since the samples are different, when we take average, then the result is more stable. And boosting, this is the another way to make the tree smooth. So gradually determine the tree. So for example, in the baseball salary example, that we have 3 groups whose averages are this, but we don't go this, but we just gradually determine the tree. So yeah, so the only, okay, so suppose the overall average is the 5.9, but then we give some values, which is the closer to 5.9, maybe the 6.1 and 6. I don't know, 5.95 and 5.8. Then, okay, so then we generate another tree. Then we gradually approach to the truth. Yeah. Okay, so the bugging, at first bugging, the more concrete algorithm. So suppose that the training set has n observations. Then repeat the following procedure for b times and bootstrap n observations. So suppose that the original data set have 6 observations, n is equal to 6, then 1, 2, 3, 4, 5, 6. Then we bootstrap the observations. So bootstrap the sample. So the result may be the 2, 3, 5, 2, 4, 3, or for example, yeah, this way. So we allow the double counts. I mean, some observation appear more than once. So we use this bootstrapped sample to estimate the tree. Then we repeat that the b times, then take average. So this, so each estimate is the f hat sub b of x. Then we take the average of this over all trees. So this is bugging. Yeah, so there are hyperparameters such as b and the maximum number of nodes for each tree. So the minimum size of terminal node. So we have some parameters. We have to determine b, or we have to determine the size of the tree. Usually we allow the smaller trees. So maximum number of nodes for each tree. Otherwise, if tree is large, then it takes more time to estimate. So anyway, we take average of many trees. So, but those. But these hyperparameters are, yeah, so yeah, generally less important. For example, the capital B, certainly it's less important because the larger B may be better, but anyway, if we take average of many trees, then results are similar. Yeah, so the typical benefit of bugging is that the boundary is smoother than one tree. So suppose that y and x have almost linear relationship, maybe too small noise, but we have this and y. Okay, so if we, okay, then we generate the multiple trees so that we make the 3 trees from the same data. Maybe, yeah. Okay, so yeah, if we make just one tree, probably, yeah, it's not clear. It's not clear. Sometimes maybe boundary is here and the average is here and here. Or maybe boundary is here and the average is here and average is here. But anyway, so the function that does not represent this, the step function that does not represent this trend. So regression tree, the bugging method, we at first bootstrap the observations. So for example, that we have 2 observations here, like this, 2 observation, and this observation twice, so just 2 observation, and this observation once, and this observation once, and the I don't know, 6 observations, so there were 2 more, right? Just 2 more. Yeah, so in this case, probably the boundary is here, and the average is here and here. But if we have another bootstrap sample, so we take 6 observations out of these 6, so maybe 1, 2, 3, 4, 5, 6. Then it's not clear, but maybe the boundary is here and average is here and here. Maybe not. Maybe probably not. Probably around here. Then average is here and average is here, maybe. So this boundary may be 10, this boundary may be 7, and the another boundary maybe 1, 2, 3, 4, 5, 6. Then boundary may be around here. Oh, sorry, that means here. And average is here, and average is here, and that may be 12. Then the bugging. The result is the average of these 3. So the obtained result is more smoother, more complicated curve. So average is probably the 7, 10, 12. So 7. So this is 7. And 10. 10 is here. And 12 is here. And if we take average of these 3 functions, probably that is like this. So bugging makes more. So bugging has a better fit than the just 1 tree, since we take average of this. So this is the idea of bugging, and the questions. So it's pretty, the straightforward idea and the convincing idea, intuitive idea. Yeah, and each tree created in bugging, unused observations are called the out-of-bag observations. For example, if there are 6 observations, 1, 2, 3, 4, 5, 6 in the training set, and the bootstrapped sample is here, 5, 1, the 3, 2, 3, 5, then the remaining set is 4, 6. So typically, third of the training set is the in the OOB observations. I don't really know the math, but yeah, so some duplications. So if we have 100 observations, then if we allow the sampling with replacement, usually about 1/3 is not sampled. So we use the OOB observations as the test set to evaluate error size. Yeah, so the mean of OOB error size is the OOB error size. And OOB error size is a good measure of test performance. So yeah, so this idea is similar to cross-validation. So if we have 100 observations, that we use 80 as training set, and training set, and 20 as test set. Then since we only use the 80 observations, we can use another 20 observations as a test set, and that is almost the, so we basically don't use the training set information to evaluate the test error. So that is a fair measure of error size for new observations. And here, out of back error estimation, it's similar idea. So it's strange that sometimes the out of back error estimation still suffer from the overfitting. So I'm not exactly sure why this happens, but still we have some trouble. But it's very similar to cross validation, logically speaking. So I don't understand 100% why this suffer from overfitting still. Yeah. So if we use all observations, of course, situation is worse since we know all observations. Then we fit those observations themselves. But out of back error estimation, it's the fair measure of the the test performance. But actually, still, it sometimes suffer from overfitting. Yeah, actually, the overfitting happens if you fit the data. I'm not exactly sure about the reason. Yeah, here we haven't studied the random forest, but okay, so yeah, so at least we can see the test error. What happens? Sorry, I don't know. Yeah, so you can see the black line. Black line is the bugging for the test error, and the blue line is the estimation of out of back error. And you can see that the out of back error is smaller than test error. So I'm not exactly sure why this happens. So so intuitively, the black line and the blue line are almost the same, but actually the black line, we have larger error. Do you come up with any reason that black one has larger error than blue one? Sorry, my Apple Pencil does not work. Yeah, I think its battery level is fine. I don't know why it doesn't work. Still, it sounds. Sorry. Yeah. Sorry, I cannot write on the pad. Yeah. So it's connected. So, sorry, maybe I cannot write. Yeah. Yeah, and this is a graph for the bugging. And this shows which predictors are more important than others. And this measure basically explains how much the variable decrease an error measure, such as the sum of squared error of regression. So if we drop the variable, the THAL on the bottom, then basically the error size, if we don't use the THAL, then error size is much larger. So that means that the THAL is the most important variable.
Sorry
Professor.
to interrupt. Oh, go ahead, Raymond.
Yeah. Oh, I was probably say the same thing, but I don't think I or anyone else can see the slides anymore.
That's what I was gonna say.
Sorry.
Yeah.
Yeah, sorry. sorry, but the yeah. So, but oh, I see. Yeah, just a moment. Yeah, actually, I cannot really write the. Oh, still you cannot see. Oh. Sorry, I'm not exactly sure what's happening. Yeah, I think maybe we can just leave this and the. Okay, so do you see the screen? Chapter 8 slides?
Yes.
Okay, great. Sorry. I don't know. At first, my Apple Pencil does not work on iPad. Then after that, actually I cannot share the screen. So I'm just using a computer now. And the variable importance measures. So so this explains the importance of the each predictors. So this explains which predictors are more important to explain the response variable. So importance of each predictor in bugging is represented by how much the variance decreases an error measure, such as the sum of squared error for regression. So the THAL, so this decreases the error the most. So, and the FPS, it does not decrease the measure too much. So these variables, the THAL, CA, or chest pain, so these variables are more important to explain the response in this case. I'm not exactly sure what this example means, but these variable predictors are more important. Yeah, so the random forest. Yeah,
how do they determine the importance? Is it like through coefficient size or the...
No, so basically we estimate another tree without the variable. So suppose we have the 13 variables, then we drop this variable. Then we fit the tree with remaining variables. Then the error size becomes larger. So we see how much the error size decreased when we introduced this variable, or how much the error increases when we drop this variable, I would say. So the tree with x1 to xp minus 1 and the tree with x1 to xp and compare, then you can see how much the last predictor xp decrease the error size. So in some way, it's similar to ANOVA. So ANOVA is also fitting two regression, y on x1 and y on x1 and x2. Then if you compare the error size of these two models, we can see how much x2 reduce the error size. So it has the similar idea to that. Yeah, and the random forests. So this is similar to bugging, except for the number of predictors allowed for each tree. In random forest, each tree is allowed to use randomly selected M predictors out of P predictors. Often, M is equal to the P over 3. So if we have 100 predictors, P is equal to 100, then M is 33. Or M is square root of P. So that is, if P is 100, M is 10. And except for that, random forests are bugging. So the idea behind random forest is to diversify the generated trees. So yeah, so it's really hard to imagine, but sometimes, okay, so X1 is a good predictor, X2 is slightly worse predictor. Then if we use all predictors, always X1 is used. So we don't have much diversity among trees. But if we randomly select the few predictors, then we use other predictors. And finally, that when we take average, then the result gets better. I cannot really imagine what's happening, but the truth is the random forest often works better than bugging. Yeah, so yeah, I don't know, probably other variables come in. So X1, X2, X3, and X1 and X2 are similar, and X1 is slightly better. Always we use X1. But possibly if we use X2 and X3, then we can improve the model or something like that. Yeah, I don't know. But the truth is that it gets better. Yeah, test error of random forests for different M's. So M is equal to P is just bugging. And M is equal to the P over 2 or square root of P. That is random forest with the smaller predictors at that time. So this is bugging. So we always use all predictors. That sounds better. But actually, this green one is better. Blue one, it's not clear. I think mostly the same as yellow one. Slightly worse, but sometimes slightly better. So almost the same. So green one is actually better. So if we use smaller number of predictors, then it gets better. So it's pretty counterintuitive, but this happens. Yeah, so yeah. So tree-based method is actually too difficult for human, I feel. But sometimes if we use this kind of counterintuitive idea, then test error gets smaller.
Quick question on that. So can we go back
Yeah,
to that slide
sure.
real quick? Sorry.
Which one?
The one we were just looking at, the error rate versus number of trees.
Error rate again is, sorry.
I believe that's what the graph we were just looking at. Where you had
the
just
last
said,
one?
Yeah, the one we were just looking at.
This one?
Yes, number of trees versus test classification error. Yeah. So let's say the error rate at 200 trees is the same at 500 trees. I know it's not exactly, but let's pretend it is. Would it be better to use less trees, or does it not matter?
The number of trees?
Yeah, so like if the error rate, you see it basically flattens out, should we use the least amount that we can?
I think the number of trees, basically larger number of trees are better. Right? So if 200 and 500, 500 is better. You mean that is the parameter capital B, right? Number of trees.
Yeah, even if the error rate stays like, let's say for the M equals P, the error rate is about flat from 100 to 500 trees. It's about the same.
Yeah.
So how many trees should we use then in that situation?
Yeah, I don't exactly sure. So as long as the graph gets flat, then that should be fine, right? So the 200 probably is enough.
Okay.
Yeah. So yeah, I think we don't have any specific theory to justify it, but as long as it gets flat, then that should be fine. Yeah.
Okay, cool. Thank you very much.
Yeah, sure.
One other question.
Yeah,
would
sure.
you use, say, like methods to reduce parameters before doing the trees, or would you do it like after? Like say to figure out which variables are not important, would you do that during the tree process, or would you say do it before?
I see. Yeah,
Like in
theoretically,
linear, we had
should
a
include
backwards
all
step.
predictors. Yeah, theoretically, we should include all predictors, I think. But probably you mean that if we put too many predictors, that's not good, right? But I think that theoretically, we should put all predictors in tree. Because anyway, the tree, they choose the best ones. So it does not hurt if you include the many predictors. So that should be fine. So if your question is, if we put too many variables, then it takes too much time or makes some error in the software package. Yeah, that may be true. But basically, we can use all predictors to generate trees. So it's not like linear regression. Linear regression, to put too many predictors, that makes trouble, right? But the regression tree, it shouldn't be a problem. Yeah, that's it. Yep. Raymond, are you convinced, or do you have more questions?
Yeah, I'm convinced.
Oh, okay, great. Yeah, so do you have any other questions?
Oh,
Okay,
me?
so
No.
no. Oh, and also the last year that I developed some videos, and the videos are more organized than my lecture probably because sometimes I retake at times. So yeah, so you can see the YouTube videos for the math 5890. Then you can see a little more organized explanation. Contents are the same.
How we should search them in YouTube? Do you have any link or other thing in
Oh,
Canvas?
the same link as the usual video, but you can go to the playlist and you can see the math 5890. And if you see the video on April 2nd or 9th, that is today's lecture, so you can see it.
Oh, thank you.
Yeah, sure.